This is Mohammad Darain Khan. I'm the team captain and the team pilot of our team, Puro Bangladesh. So right now, we are demonstrating our first mission, autonomous 8-loop circle. The drone will autonomously take off and complete the 8-loop circle through these two poles according the demonstration guideline, and then it will autonomously land in the landing zone. So let's get started. Okay.
Auto flight mode. Loiter flight mode.
Arming the
flight
drone.
mode. Arm. Auto mode not armable. Fence _ auto enable is 1. Will be removed in 4.7. Use 3. Stabilize flight mode. Armed. Auto flight mode.
Our team is organized into 5 specialized divisions for our UAV development. The mechanical division handles airframe design, manufacturing, assembly, and payload integration. The electrical division is responsible for the power system, wirings, sensor, and electronics integration. The research and development division performs design validation, testing, and performance optimization. The marketing division manages sponsorship, documents, and public outreach, while the logistic division procurement, inventory, and project coordination. The team captain additionally leads all software development, autonomous mission planning, and flight testing, while serving as the primary UAV pilot. This is the final mechanical design of our UAV. Here we can see the complete technical drawing, including the front, right, top, and perspective views with all important dimensions. The overall frame measures 515 mm in width, 483 mm in length, and 394 mm in height. The UAV is built on a foldable quadcopter frame using 16 mm carbon fiber arms. We have used RJX Hobby Z16 foldable arm connector for the folding arm mechanism. Carbon fiber provides high strength while keeping the overall weight low. The foldable arm design also makes the UAV easier to transport and store. The landing gear was designed to provide sufficient ground clearance for the payload release mechanism and to ensure stable takeoff and landing. We also designed a canopy for the drone for electrical enclosure. During the mechanical design process, special attention was given to component placement. Heavy components such as the battery pack, Peacock flight controller, Raspberry Pi, and payload mechanism are positioned close to the center of the frame. This improves weight distribution, minimizes the vibration, and provides better stability during autonomous flight. The weight table shows the weight of every major component used in the UAV. The empty weight of the aircraft is approximately 2.34 kilograms, while the maximum takeoff weight, including both payload, is approximately 3.5 kg. After the final assembly, the center of the gravity was calculated and verified experimentally. The battery position was optimized so that the center of gravity remains close to the geometric center of the UAV. A dedicated storage box was designed for safe transportation of the UAV. The material we have chosen for the box was carbon fiber. The box was securely holds the airframe, batteries, propellers, and accessories, protecting the system from damage during transportation and field operation. In this section, we will present the manufacturing and assembly process of our UAV. The main structure is built using 16 mm carbon fiber tubes and 1.5 mm carbon fiber sheets. The carbon fiber sheets were supplied in 200 by 200 mm panels, were cut into the required chassis plates, motor mounts, and structural components using CNC machine. Custom parts such as the payload mechanism and supporting brackets were manufactured using 3D printing. Before assembly, every part was checked to ensure proper dimension and fitting. Throughout the development process, we documented every stage of manufacturing and assembly. These visuals show the complete workflow, including carbon fiber sheet cutting, tube preparation, part fabrication, frame assembly, electronics installation, payload integration, and final assembled UAV. We have used CNC routing machine to cut the carbon fiber sheets and draw the geometry, which we have designed in the CAD software, and we have used CNC lathe machine to cut the carbon fiber tubes for our drone arms. The fuselage was designed with a compact and streamlined profile to reduce aerodynamic drag while providing sufficient space for the avionics power system and payload mechanism. The carbon fiber structure provides high strength while keeping the UAV lightweight. The modular design also allows components such as the motors, ESC batteries, landing gear, and payload mechanism to be replaced individually, making maintenance faster and easier. For motion control, we use 4 T-motor MN4006 brushless motors with 15-inch T-motor carbon fiber propellers. Since this is a rotary wing UAV, flight control is achieved by varying the speed of individual motors. The landing gear provides sufficient ground clearance for the payload mechanism while ensuring stable takeoff and landing. The assembly process begins with the chassis and carbon fiber arms, followed by the propulsion system, avionics power system, communication modules, sensor, and finally the payload mechanism. After assembly, wiring, calibration, and system integration are completed before ground testing and flight validation. This is our mission mechanism system, a dual payload drop system mounted underneath the UAV frame. The system consists of 2 identical release mechanisms, each having a compact size of 118 by 34 mm. The parts are manufactured using FDM printing with ABS material. Each mechanism can securely carry a payload of 623 grams, giving the UAV a total payload carrying capacity of 1246 grams. The mechanism is very simple. For the release system, we use DF Robot 6430mm push rod linear actuators. This actuator locks the payload during flight and release it by retracting the holding mechanism. The actuators are powered separately with a stable 6-volt power supply from Holybro UBEC 3-12S module. Since these linear actuators do not support direct PWM control, we integrated 2 PWM relay modules. The flight controller sends the PWM signal to these relays, allowing both payload mechanisms to be controlled independently. To maximize the target detection accuracy, the camera is mounted in a fixed downward facing position. During operation, the first actuator retracts and releases the first payload. After that, the second actuator works separately and releases the second payload. This independent release system allows us to deliver both payloads accurately according to the mission requirements. To ensure reliability, we perform repeated activation tests with a complete mechanism. The locking system keeps the payload firmly attached during movement and vibration, preventing unwanted release during flight, while ensuring a smooth and successful drop when activated. The avionics system of our UAV was designed with a modular architecture where each subsystem is connected to ensure reliable flight control. At the center of the system, we use a Holybro Pixoc 6X flight controller, which handles flight stabilization, sensor processing, and motor control. A Raspberry Pi 5 integrated with a Raspberry Pi AI camera works as the onboard companion computer for image processing and autonomous mission execution. The communication between the Raspberry Pi and Pixoc is established using the Mavlink protocol. For navigation and control, the Pixoc receives data from onboard sensor, including the GPS module and internal flight sensors. Manual control is provided through the Radiomaster GX12 transmitter with XR4 Gemini crossband dual-band Express LRS receiver. The CHM30 air unit is used for telemetry and Ethernet communication, allowing data transfer between the UAV and the ground station. The propulsion system consists of T-motor MN4006 motors with 15-inch T-motor propeller controlled by a Hobbywing X-rotor 8TMs 4-in-1 8S ESC. Power is supplied from a custom 6S1P battery pack built using EVE 50PL INR 21700 5000 mAh cells. The Holybro PM02D power module monitors battery voltage and current while providing power to the Pixoc 6X. Different voltage levels are distributed according to subsystem requirements. A Holybro 5A UBEC provides regulated 5-volt power to the Raspberry Pi 5. The CHM30 air unit receives 16 volt through an LM2596 DC to DC buck converter. A Holybro 3-12S UBEC provides 6 volt power to the 2 DF Robot linear actuator used in the payload mechanism. The complete power system is
controlled through an Autoro AS100 electronic power switch, allowing safe power activation from a single point. We also have two PWM relay module for the actuators, as the DF robot linear actuators are the DC actuator and there is no PWM signal link in the actuator. The integration process started with the propulsion system assembly, where the motors were soldered and connected with the ESC. After completing the propulsion wiring, the power distribution system was assembled and the required voltage output were verified before connecting the avionics equipment. The PIXOC 6X was then mounted at the center of the frame using vibration isolating dampers. The Raspberry Pi, GPS module, receiver, CHM30 air unit, and the payload control system were installed according to the design layout. All power and communication connections were organized through dedicated cable paths and secured properly to reduce vibration-related issues. We have used vibration isolating dampers for PIXOC 6X, as well as we have also used the vibration isolating dampers for the ESC. The software system of our UAV is divided into three main parts: flight control, onboard processing, and the ground control. The flight control system is handled by the Holybro PIXOC 6X, which controls flight stabilization, navigation, and autonomous mission execution. For onboard processing, we use a Raspberry Pi 5 connected with a Raspberry Pi AI camera. The Raspberry Pi processes camera data during flight and communicates with the PIXOC through the Mavlink protocol. For the first mission, the flight path and mission parameters are prepared using Q-ground control and uploaded to flight controller before takeoff. During the takeoff, the ground station continuously monitors UAV status, including position, altitude, battery information, and mission progress through the CHM30 communication link. For the second mission, UAV reached the required search altitude and starts scanning the mission area using the onboard camera. Each captured image is processed on the Raspberry Pi. The image is first converted to RGB to HSV color space for better color detection under different lighting conditions. The software then applies color filtering, contour detection, and shape recognition to identify the required mission targets, including the red triangle and blue hexagon. After detecting a valid target, the system calculates the target position and sends the required commands to the PIXOC using Mavlink protocol. The UAV then moves toward the detected target, descends to the release altitude, activates the payload mechanism, and delivers the payload. After completing the first delivery, it climbs back to the search altitude and repeats the same process for the second target. Once both payloads are successfully delivered, the UAV returns to the home position and performs an automatic landing. During the entire mission, the PIXOC combines data from GPS, IMU, barometer, and magnetometer to calculate the UAV's position and orientation. We have performed a series of subsystem tests of our UAV. First of all, we conducted a structural strength test by applying a 3 kg load on the upper chassis plate. The structure successfully withstood applied load without any visible deformation or damage. Next, we have performed a thrust test to verify that the propulsion system could safely lift the UAV at its maximum takeoff weight. The propulsion system generated sufficient thrust for stable flight and payload operations. We also carried out two hover tests to evaluate flight stability. One is with payload and another one is without payload. The UAV maintained a stable hover in these two tests. Finally, the payload release mechanism was tested repeatedly to verify reliable operation. Both payloads were released independently and successfully without any mechanical failure. We selected a compact X-frame configuration which provides balanced weight distribution and minimized aerodynamic drag during flight. To meet our mission requirements, we selected the T-Motor MN4006 motors with 15-inch propellers. Before finalizing the propulsion system, we analyzed the manufacturer's thrust and efficiency data. As shown in the thrust curve, thrust increases almost linearly with throttle reaching over 2.2 kilograms per motor at full throttle. This provides sufficient lift to safely carry our maximum takeoff weight with adequate thrust. To verify the design, we analyzed data from real flight logs. The roll, pitch, and yaw responses show that the UAV remains stable during hover, turning, and autonomous flight. The UAV has an empty weight of 2.3 kilograms and a maximum takeoff weight of 3.5 kilograms. It can carry a maximum payload of 1.2 kilograms, powered by a custom-built 6S1P 5000 mAh battery pack. The UAV achieved a maximum endurance of 10 minutes without payload and 6 minutes with the full payload during flight testing. At its normal cruising speed, the UAV provides an operational range of approximate 4.8 kilometers with payload. To ensure flight safety, all avionics components are securely mounted inside the UAV. The PIXOC 6X is installed on vibration isolating dampers to reduce vibration during flight. All power and communication cables are routed through dedicated cable paths and secured with cable
durable ties and protective sleeving. This prevents loose connection, reduces electrical interference, and make the maintenance easier. A low ESR capacitor is installed across the ESC power input, PM02D power module, AS100 switch to reduce voltage spikes and electrical noise. This helps to protect the ESC, flight controller, power module, and the switch, especially during the rapid throttle changes. For electrical safety, the UAV is equipped with an Autoro AS100 electronic power switch for safe power control and a little fuse Mega 80 amps fuse to protect the system from overcurrent. The UAV also includes a fail-safe system. If the RC signal is lost during flight, the flight controller automatically switches to return to launch mode, allowing the UAV to return safely and land without pilot intervention. After submitting our PPR report, we further optimized the UAV based on real-world testing and component availability. We officially documented all these changes and submitted a detailed design report to TEKNOFEST organizers.